Hi guys, it's Mr. Ng, and I wanted to make you a short video to walk you through your rotational inertia lab, your T-pose lab. So your big output, your big dependent variable for the rotational inertia lab, for your T-pose lab, is basically I, the moment of inertia. So here, here we go. I is the moment of inertia, and if you recall, the moment of inertia could be all sorts of equations, but the base equation is going to be something around mr squared, right? If you recall, we have little fractions in front of it, 1/2 mr squared, 2/5 mr squared, depending on the shape, right? Because the moment of inertia, it's so much more difficult than mass, because with mass we just measure the mass, it doesn't matter what shape. But with the moment of inertia, a stick versus a mug or my controller, they all have different moments of inertia. So here, this is what we're trying to get to, the relationship between mass and radius in the moment of inertia. To get there, we're going to have to do a little bit of math. We're going to have to prove this little equation in the box by going through a lab. So here, there's some raw equations we needed for the lab. Number one, we needed to know all of our torque formulas. Torque is equal to force perpendicular times the radius. We did this in all of our little math exercises. On top of that, torque is equal to the moment of inertia times alpha. And we can use this equation to solve for the moment of inertia. That means the moment of inertia is equal to basically torque times alpha. We're going to use this to solve for the moments of inertia, right? Meaning all we need is number one, torque, and number two, the moment of inertia. So here, let's first solve for torque, the torque of our system. If we recall, our system had a little T-pose, right? And there was a little string on it, and there was a hanging mass, and as that hanging mass fell down, it spun your little PVC T-pose thing, right? So if we do a free body diagram of this hanging mass, let's look at that. You'll find that the bottom vector is mg, and the vector pulling the weight up is tension. And that tension, let's look at this. Let's look at that little circly part, that PVC. Let's bring that PVC and look at it this way. The PVC pipe has that very same tension pulling on it. In fact, that tension is the perpendicular force that we mentioned in this formula here. In the formula where torque is equal to the perpendicular force times the radius. So all we need to do is take this torque and multiply it by the radius, right? The radius of the little PVC pipe. It's going to be tiny. It's going to be like 1.1 centimeters. But finding that tension is a little bit difficult. So here, this tension, well, what is that tension? It's not mg. If it was mg, the mass wouldn't fall down. So we're going to need to do some sum of forces. So here, the sum of forces is equal to, the tension's positive, the mg is negative, and it's going to equal to ma. Is this ma positive or negative? You could pause it. No, you don't have to pause it. It's negative, right? It's falling down, right? So all we got to do is solve for tension. Tension is equal to mg minus ma. That means tension is equal to m times g minus a. And if that tension is m times g minus a, then the torque is basically the tension times r, or the torque is equal to m times g minus a times r. So now we know the mass, right? We know the hanging mass, we measured that. We know g, that's 9.8 meters a second squared. A we can solve for if we have the time. And we know the radius is that little bit, probably around 1.1 centimeters. We're halfway done. So now we have the torque done. Good. So now we need to figure out the angular acceleration. So how do we do the math for the angular acceleration? Well, we know a formula. We know that the tangential acceleration is equal to the angular acceleration times r. So that means the angular acceleration is the tangential acceleration divided by r. That's pretty easy. Hey, this acceleration is the exact same a here. So that's our last bit. We need to find the tangential acceleration. And if we recall our old school kinematics equation, distance is equal to 1/2 at squared, right? Especially only if the initial velocity is 0, which it was, right? The mass wasn't moving, and then you let it drop. So that means a is equal to 2h divided by t squared. That will solve for a. So a lot of little equations. First, we're going to solve for the tangential acceleration. Then we're going to plug this a into this equation and this equation to find the torque and the angular acceleration. And then finally, this is ugly, we could find the moment of inertia by dividing torque by the angular acceleration. A lot to do. So let's work through that a little at a time. Sounds like our first step is to find the tangential acceleration. So here's some data that a student shared with me. Thank you very much, Jonah. So here, Jonah was kind enough to organize all of the data into different masses, as you can see down here, and different radii. I already did the math a little bit, but here, let's start over so that I can walk you through it. First things first, we need to find the tangential acceleration. So if you don't know how to set this up, just start with A1, type in your masses, type in the times that you got for your little mass to fall down, and that's all the data that you need. So here, let's solve for the tangential acceleration. I know how to spell. Okay, so if you go back here, back to our our tangential acceleration is equal to 2h divided by t squared. 2h divided by t squared. 2h, the height was around 1 meter, right? And then the time is right here. So our magical button in Google Sheets is equal to 2h, 2 times the height. So 2 times, this is shift 8, this is a little asterisk, h. You know, I'm not going to click on this cell. Now if I click on that cell, it's going to change as I go down. So I'm not going to click on it. I'm just going to type in 0.9 because that number is static, right? The height that it fell is going to stay the same. Okay, I'm going to put this in parentheses. So I'm going to click here, open parentheses, and then we're going to divide this by t squared. Divided by, I'm going to do parentheses again. Here's my time. To do squared, you have two options. You can multiply it by itself, b2 times b2. Or if you want to be fancy pants, you could do the caret, which is shift 6 to close parentheses. Okay, I'm going to press enter. That's Google Sheets solving it for me. And now I can just click on this. And if I drag it down, look at this little cursor here. See how I have a hand? The hand's no good. That moves things. See how I have a pointer? That just selects things. If I go right here above my little dot, it becomes a cross. That's great. I'm going to hold down and drag down. Good? If that procedure is difficult for you, like you have a laptop and it's hard for you, then you could just hover above this. You could do copy and then highlight the whole bit on the bottom and then do paste. Same thing, it'll copy and paste that formula. I have my tangential accelerations. Good. So what's the next step? We probably need the torque, right? So let's go to the torque. So here, let's go back to our little whiteboard. My torque is mass times g minus a times r. M times g minus a times r. That's going to be our torque. So let's solve for torque. My torque, E, is equal to mass, all right? This is the mass, times, so you need to do that little asterisk. If you don't, Google gets confused. G minus a, so 9.8, that's g, that's acceleration of gravity, minus a, it's this a, close parentheses, times r. R is a constant, it's not going to change, so I'm just going to type it in, 0.011. Boom. Good. Same thing, I just have to drag this down, like so. There you go. And then finally, I need my angular acceleration. Okay, my angular acceleration, let's go back to our formula. My angular acceleration is just the tangential acceleration divided by r. How easy is that? So let's go back here. That means this is equal to my tangential acceleration divided by my r, which is 0.011. Boom. I'm just gonna drag this down again. Okay, so the moment of truth, we just need our moments of inertia. And as you recall, the moment of inertia is right here. It's torque divided by the angular acceleration. So here, this is equal to my torque, which is right here, divided by the angular acceleration, which is right here. Boom. Don't freak out if it says 0. Chances are you probably don't have it all neat like this. You probably have a bunch of huge numbers here. Let me undo the formatting. So more format, clear formatting. Format, clear formatting. Ugh. All right, whatever. Yeah. Automatic is equal to the torque divided by the angular acceleration. And then you have these ugly numbers, right? So I'm just a stickler for having a neat sheet. This is just so ugly. It's got all these numbers. So typically I go over here and I just make it a number. That's fine. That just makes it a lot prettier. It doesn't lose any value. Like it didn't estimate it for you. It just hid all the ugliness. So here, now we just have to graph it. And when we graph it, our mass is going to be our independent variable, meaning our mass is our x-axis, and then our moments of inertia is going to be our y-axis. So there are two ways to do this. There are many ways to do this. What I like to do is I like to hold down control. I'm going to highlight my mass and then highlight my moments of inertia by holding down control. But look, I got this stupid box here. There you go, get rid of that box. So here, just these two guys are highlighted. Then I can do an insert chart. If that's a little bit cumbersome for you, then you could highlight this, control copy, and then do a paste special and just paste only the values. You have to do values only. If you paste the formulas, it's gonna mess up. Watch. Here, I'm gonna try that without doing values. I'm gonna do control C, control V. It's oh craziness because you moved over some formulas, right? And the formulas, they don't match to that space. So instead, control Z, you could do a copy, and then you could go here, and then you could do paste special, paste values, okay? And then here, let's make them look, I don't even need them to look nice, to be honest, right? I just have to graph it. So here, I'm gonna highlight these two, right? Notice that I did my X first and my Y second. That's the way Google likes it. I'm gonna go here, insert a chart, and look, I have a very nice chart already. But if you don't have it nice already, because I already kind of did a trial run, if it's doing like craziness, Google tends to like give you a column for some reason. Go to chart type, go to scroll down, go to a scatter plot. That's good. Make sure your x-axis is the mass. Make sure your y-axis is your moments of inertia. Okay, and here this looks real good. All I gotta do is I gotta go to customize. I'm gonna go down to, I don't want my chart titles, I want my series. I want a trend line, and I know it's linear, and it's got a pretty linear trend line, which is expected. All right, for mass, you're supposed to get a linear relationship. Look at that, I'm giving you guys all the answers because I'm not there. Okay, try it again for radius, right? So here I have another set of data for radii. Go through the exact same procedures. Find the tangential acceleration. Right? Find the torque. And then finally find the angular acceleration. And then finally your coup de grace, finally your moment of inertia. Okay, this is kind of ugly. I do a little thing where I highlight this, I go to format, I do wrap. That looks nicer. Okay, I hope that helps. I will be making a short video to do the radius also, but I recommend just kind of working off this video and trying to transfer that knowledge to do the radius on your own, and you should get an exponential graph. Okay. Hey, thank you very much for watching.